Okay, it's 10:40. Let's start. Attention, everyone, please. And yeah, it's nice to see so many of you here on this beautiful sunny day. Just as Kenny noted a couple of lectures ago, it's not the best day for electrostatics because there are lots of drops of water in the air which make charged objects lose charge. So, a couple of announcements. In principle, I made those announcements by email, but I'll just repeat that the first homework is available and the deadline is for Sunday. Please access this first homework by clicking the respective link on Canvas. Do not get onto Expert TA first and then launch it from there, because then your scores may not get transferred to Canvas properly. And after this lecture, I'll have office hours. Normally, office hours are on Monday and Friday, but because Monday was a holiday, we're going to have an office hour today. If that makes sense, we'll start talking about physics. And, well, the relevant physics concept is electric fields. It's something we started discussing last week, and something that we discussed quite briefly. Well, just as a reminder, an electric field is a property of a charged object which describes its ability to interact with other charges. So let's say this is a charged object and it's got charges in it. So let's say there are lots of negative charges. There could be some positive charges somewhere, more negative charges. It could be a piece of amber, it could be a piece of rubber, something dielectric with a charged pin just there. And the way we probe the ability of this charged object to interact with charges is bringing a test charge. So this is a test charge Q. Once we place it near the object, it will experience some force acting on it, force F. And we showed last time that the ratio F over Q is independent of the charge Q. Well, if it's independent of charge Q, then it's a convenient characteristic of the properties of that charged body at this particular point. And, well, there's a name for it. That's the electric field. E equals F divided by Q. And, so the definition of the electric field is that at test charge Q is acted upon by a force F, which is proportional to that charge, and E is the characteristic of that charged object at that point in space. I'll put this in a red frame. You know what that means. A question. Oh, sorry. Is that better? Yeah. The guys in the back, is it good? All right. If at some point during the lecture I cannot be heard clearly, do let me know. A question.
Sorry, what did you mean by independent of Q?
It means that it's going to be the same for all values of charge Q? Well, in principle, if we have two interacting objects, and or one of those objects has a certain quantitative property, such as the charge Q, then in principle, to characterize all their possible interactions, one would need to specify the force acting on it for all possible values of that charge Q. But it turns out there's no need to, because this f of Q, this ratio of f divided by Q, it's going to be the same for all values of Q. And that's why it's convenient to introduce this ratio, which is a vector, which is the electric field at this point. And last quarter in physics 5a, you talked perhaps about gravitational fields. Well, you may or may not have it. If you haven't, it's all right. Don't panic. So it's not strictly speaking needed, or could be just revised relatively easily. But so gravitational fields, it's a field that a gravitating object creates around it, and which describes the ability of that object to interact with other objects which are masses. And the electric field is quite similar, just instead of the ability to participate in gravitational interactions, it describes the ability of a charged object to interact with charges. And to gain some intuition about what it looks like, let's start with an example. Let's start with the electric fields of just one point charge, one particle. Let this particle be a proton. So I'll write here an example. The electric field of a proton, which is a nucleus of a hydrogen atom. So let's say this is our proton. Its charge is Qp, as we know it. And we consider some point distance r away from this proton. And let's, to be specific, put a positive charge Q at this point. Well, if we do, there will be some force F acting on it. And in principle, to find the electric field at this point, it can also be a negative charge. We can put a negative charge there. The electric field we're going to find is still going to be the same. Well, we know that force F, right? We know it from Coulomb's law. It's given by the constant K, the charge Qp, which is positive, charge Q, which is also positive. That's why I'm not writing absolute values, divided by distance squared and multiplied by a unit vector in the direction along the line connecting the two charges and away from the proton. So this vector r hat is directed like this, and it's a unit vector as usual. So this force, this equation for the force, consists of two parts. So the first part, which describes the magnitude of the force and given by Coulomb's law, and the second part, which shows its direction. Well, the fields then of the electric field E, is given by the ratio F over Q. And according to the above formula, it's KQP over R squared r. A question? No. So what we see is that the electric field of a proton is directed everywhere away from that proton. So this is our proton. The electric field at this point is directed here, and it obviously, according to this formula, depends on the point in which we measure it. So it's like this here. At this point, it's again directed away from the proton. And here. All right. So that's the direction of the electric field at all points in space. It's everywhere away from the proton. It's positively charged. If it was negatively charged, it would be in the opposite direction. Well, as you can see, it's different everywhere. Well, to get some feeling about the magnitude of the field, let's compute it at a given distance. And well, before we compute it, we've got to perhaps think for a brief while about the dimension of the electric field, because we know that every physical quantity has got a dimension. And well, let's figure out the dimension of the electric field. So EQ equals F. And we know that the force F is measured in newtons, charge is measured in coulombs, and we've got to multiply coulombs by something that will give newtons. And well, that something is going to be newtons over coulombs. So that should be the dimension of electric field. Well, let me write it upstairs. Newton over coulomb, that's the units. Of electric field. And when you do calculations, please make sure that you've got the right units, and just track the dimensions of all equations in your answer. Well, now we know the units. Let's compute, say, the field, the electric field of a proton at a distance of 1 micron. It's going to be given by the length of this vector, that is the absolute value of E, is going to be given by this prefactor, because the length of the unit vector is unity by definition. So it's KQP over R squared. And let's plug in the numbers. 9 multiplied by 10 to the 9 Newton meter squared over Coulomb squared. That the charge of a proton, 1.6 multiplied by 10 to the minus 9, so 10 to the minus 19 coulombs. Basically, it's known as elementary charge, also the charge of an electron with the plus sign, divided by R squared, 1 micron, also known as micrometer. It's 10 to the minus 6 meters squared. So we plug in the numbers. That's 1440 newtons over coulomb. And the electric field is the same for the same R, meaning the magnitude of the electric field is the same for the same R. Right, are there any questions about this? Not that I can see. Well, what we have found here, we've found basically the electric field of a point charge. Let me write here, electric field of a point charge. I was talking about a proton here, but the calculation of the electric field of just a point particle with a charge everywhere in space is exactly the same. We just need to replace the charge QP by the charge of that particle, and the result is E equals K Q over R squared R hat. If the charge Q is positive, then it's directed everywhere away from that charge, like it is for proton, like it is shown here. If it's negative, then it's directed everywhere towards that charge. Well, we'll see a couple of pictures maybe in 5 minutes. All right? Okay, now what if we have multiple charges? So we started that discussion with the notion of an electric field of an arbitrary charged body. I'll write here multiple charges. So an arbitrary body has got multiple charges. So let's say this is our charged body, and there are charges here, Q1, Q2, Q3, and so on. They could be both positive and negative. If we consider an arbitrary point somewhere in space, then charge Q1 creates an electric field at this point, and well, its electric field is K Q1 over R1 squared, where R1 is the distance to that charge from this point, R1 hat, where R1 hat, it's a vector along the line pointing away from charge 1. And I've shown the direction of this field as if this charge Q1 was positive, but the equation applies for both positive and negative Q1. And the same for charge Q2, that's going to be the same expression, just with 1 replaced by 2, K Q2 over R2 squared R2. And because both of those charges create forces on the test charge, which add up, their electric fields also add up. And I can write actually a formula that I wrote at the end of the previous lecture. So the electric field of multiple charges is given by K Q1 over R1 squared. R1 hat, so that's an electric field at a given point. R1 is the distance to it from charge 1. Similarly, the contribution of charge 2 R3 squared R3 and so on. So what this equation says here, and we derived it last time, it says that the electric field at a given point, electric fields created by multiple sources, which in our case are different charges, is given by the vector sums of the respective contributions. So E1, the electric field of source 1, as if it existed independently, E2, electric field of source 2, and so on. So electric fields add up. And this principle of addition has got a special name. You may or may not have heard this name in Physics 5a, but it's called the principle of superposition. Principle of superposition. The principle of superposition, it's a generic principle in physics, according to which vector quantities of the same nature add up. Let me put it this way. Certain vector quantities, such as electric fields, gravitational fields, forces, later we will learn magnetic fields, can be added up, meaning the resulting field at a given point is given by the sums of contributions of individual sources. And whenever they could be added up as vectors, it's called a principle of superposition. And in electricity and magnetism, we're going to have a lot of that. That's why it's important to be able to add up vectors. So it's going to be just an important skill used to compute electric fields and magnetic fields and all kinds of fields that have this principle. Well, all that brings us to the question of how we visualize electric fields around charged objects. Because we see that electric fields around the same object are different at different points. And strictly speaking, to specify the electric field around some complicated object that has got multiple charges in it, we would need to specify a vector at each point in space, which would be impracticable in principle, because we can't specify an infinite number of quantities. But there are certain graphical conventions that allow one to illustrate electric fields. So this is simulation in what is called FED. It's on the website of University of Colorado, and they've got a library of such simulations. So this is an illustration of an electric field. So let's say we've got a charge here, it's +1 nanocoulomb. And although we cannot draw an arrow at each point in space, we can just draw them with some finite density, meaning we can specify a grid in space, and at each point of the grid just draw an arrow which will indicate the direction of the field. And that will give us a picture that will illustrate what this field looks like. So that's the electric field of a positive charge. And there's this thing called sensor here. That's a test charge. You can think about it as a test charge. There's a force acting on it. And the closer we bring the test charge to this positive charge with probe, the larger the force, because the force depends on distance as 1 over r squared. So it diverges, it becomes infinite at the location of the charge itself, and it's quite small away from it, and it's always directed away from this charge. Now, if I remove that, similarly for a negative charge, we've got a similar electric field, similar pattern of fields, but now it's directed towards the charge. The magnitude is the same, only the direction is different. All right. A question. Oh, it's just a convention they make. So a sensor here is a positive charge, so they needed to pick some sign of that charge, and they picked a positive one here. Just arbitrary, no particular reason. A question.
Will we ever have to do test charges that are negative, or is it always going to be positive?
Yeah, if it's a test charge and some abstract charge that you want to consider just to find the electric field, then you are safe with always considering a positive one. If it's a realistic experiment, say you literally have a charge, like in the original Coulomb's experiment, then you have to work with whatever charge you have, and then it could be arbitrary.
I assume you just assume the test charge is positive, so that if you have a negative charge in the actual interaction, you can just swap
Yeah.
signs of the numbers and it all works out. If every charge is positive, that makes it easier to just sort of
Yeah.
consistently do the same thing every time, right?
Right. Yeah.
That makes sense.
Yeah. Then you don't have to do an extra action of reverting the sign due to this yellow guy being negative. It's indeed more convenient. So there's where the electric fields of point charges, positive and negative. We can consider more sophisticated configurations, say one positive, one negative. And that's what the field around it is going to look like. And this configuration of a positive and a negative charge is called a dipole. Well, let me switch back to the document camera for a second. I'll write here electric field lines. And I haven't yet explained what it is. It's just a subtitle. And in that context, I would like to give some motivation for considering a configuration of two charges, one of which is positive, the other is negative. It happens quite commonly in diatomic molecules. So what can happen, when two different atoms combine into a molecule, say an atom of sodium and an atom of chlorine, which is bigger, it's got a bigger core. So when they combine, they form a molecule of sodium chloride, also known as salt. Chlorine pulls one electron, it's got a bigger nucleus, it pulls one electron from sodium, and so what happens before they bind, they are both neutral. When they form a bond, chlorine steals an electron from sodium and it acquires a charge of E. Well then, here we've got sorry, it's still an electron, so it's minus E. Here we've got plus the absolute value of E. So it's got a positive charge here, negative charge here, and this combination of charges, plus Q minus Q, that's called a dipole or an electric dipole. And I'll go back to the presentation. So that's what the electric field of a dipole looks like. Near the positive charge, very close to it, the electric field is very similar to just that charge in isolation. There's going to be a big electric field directed away from it, which diverges, that is, becomes infinite as we approach that charge. But further away from this field, it gets distorted by the presence of the negative charge. And again, close to the negative charge, it's directed towards that negative charge, and at short distances, it's weakly disturbed by this positive charge. And at large distances, distances significantly exceeding the separation between them. So let me make a smaller dipole. The field is very small. It practically vanishes because these two guys at large distances compensate each other to a large extent. And that's what the electric field of a lot of diatomic molecules looks like. So, and again, that's called an electric dipole. A question?
Sorry, so the field gets smaller the closer the particles are together?
At a given large distance away from them, yes.
Okay.
And I can make even just a more specific statement. It's proportional to the separation between them at large distances.
Why does it disappear after a certain distance? And why is that distance shorter when there's two of them as opposed to...
This presentation is a bit misleading. It does not strictly disappear. It's just they fade those arrows to show the amplitude, but it's finite at all distances. It just gets very small, and it decays with distance as 1 over r cubed at very large distances for any particular direction. But it's always there. It's strictly speaking, it's finite, meaning non-zero at all points in space.
So does the amplitude reduce faster when there's a dipole than if there's just a single charge, or not?
That's right, because we know the electric field of a single charge decays as 1 over r squared, but when we add a negative charge to a positive charge and look at them from large distance, they, to a good approximation, cancel each other's effects, because the distances are approximately the same, but the charges are different, so they balance each other out.
That makes a lot more sense. Thank you.
All right. Also maybe we can also look at the electric field of a bigger positive charge and a smaller negative charge. The way I can do it in this simulation is just overlap multiple positive charges. So I put another positive charge on top, to another one on top, and another one, and another one. Now it's 5 nanocoulombs according to this legend, minus 1 nanocoulomb here. And what we see here is in a bigger region of space, the field of this positive charge looks very close to the field of that charge just in isolation, because this negative charge is significantly smaller. It's 5 times smaller, and it weaker perturbs the fields of this guy in a big region of space, but still very close to the negative charge. Still, it will look like the electric field of this negative charge. All right. And in this presentation, you can create multiple configurations of charges. The link to this simulation is on Canvas. It's in the subsection extra materials and handouts in the modules. So this configuration of 4 charges, one of which, two of which are negative, two positive, it's called a quadrupole. You do not necessarily have to memorize it. It's just for the sake of knowledge, I wanted to mention this at least once. So that's called a quadrupole, and it could also describe molecules that would consist of 2 atoms of one kind bind this way to atoms of another kind here. All right. So that's what electric fields look like, and maybe closely connected to them, I'd like to mention another concept. That's the concept of electric field lines. So I'll switch to the document camera again. So drawing arrows like this in the illustration in the presentation we just saw, it's one way to show electric fields. But it can be also convenient sometimes to draw solid lines for these arrows. So this is the electric field of a positive charge, and let's disregard this black circles here. But those red lines show the direction of the electric field everywhere, and it's as if we drew those arrows like in the simulation, but we just draw solid lines through them, and those red lines are called the electric field lines. And this is again the electric field of a dipole, positive charge, negative charge. And in principle, we solve that electric field, but now imagine that we drew solid red lines through those white lines in the illustration, and that's the picture we're going to see. And that's usually how electric fields are shown. So those are also electric field lines. Now for the case of a dipole. And because the electric field is directed away from the positive charge and towards the negative charge, all the electric fields, all the electric field lines are going to be emanating from the positive charge and ending at the negative charge. And the same statement applies to the cases when we've got multiple charges. Well, here's another situation. There are 2 positive charges. So I can switch back to the simulation. So that's what it would look like if we drew arrows, and then we draw solid lines through those arrows, and that's the picture we see. This one here, and this is another picture corresponding to a bigger positive charge and a smaller negative charge. So if the plus one is significantly bigger, then again we can see that the electric field is significantly stronger near it, and it gets perturbed only close to the negative one. All right. That's quite arbitrary, because strictly speaking, to show the whole field, we would need to draw them through each point in space, and it's a little bit arbitrary. That's an important point that I'd like to emphasize, is that although we draw them with a finite density, they exist everywhere. Some people who never had physics just have a misconception when they hear about electric field or magnetic field. They sometimes think about magnetic field lines or electric field lines, which have a finite density in space. At one point we have a field line, at another point we don't. But so the electric field exists strictly everywhere. It just in pictures we draw them with a finite density at selected points, and a very common convention is to draw them with such a density that their density near a given point is proportional to the magnitude of the electric field. That's why here we've got more lines that they're denser, that there's going to be a stronger electric field here than here. And again, that's a convention, but it's a bit arbitrary. All right? A question? Only if it's positive and negative, and if their magnitudes match. Otherwise, it's not called a dipole. Okay. All right. If that makes sense, let's talk a little bit about the effects of an electric field. So again, when we put a charge next to a charged body, there's going to be a force acting on this test charge, and this force will make it move. So I'll write here the dynamics of charges in an electric field. Okay, so let's say we've got a charged body, put a charge Q next to it, and as a result some force F equal to QE acting on it. And if this particle with charge q isn't pinned, if it's not held by anything, if it's not localized, it can move as a result of this force. And so it means it will be accelerated. According to Newton's second law, if it's a free particle, if it's not attached to anything, the same force is given by the mass of that particle multiplied by its acceleration. Well, just to emphasize that it's not always the situation we're going to have, because if it's literally an experiment in which you measure the electric field, you will be holding that charged particle of charge q and mass m, and then it's not free to move. But if it is free to move, so then that's its acceleration, and from these two equations, we've got ma, mass times acceleration, it's qe, and the acceleration is q over me. Now, we also know from the course on mechanics, from physics 5a, that the acceleration of a particle is the derivative of its velocity. And we therefore got an equation like this: dv over dt equals q over me. Well, those who already had a discussion section had an exercise on that, a bonus question about dipoles, and just a regular question about a particle accelerated by an electric field. So this is the equation, or what one also says a differential equation, because it involves the derivative of a particle, of a quantity that needs to be found. We can rewrite that as dv, which is an infinitesimal change of velocity on some infinitesimal time dt. We can rewrite it like this. And we can take the integral, or as one says, integrate this equation. Well, this is a constant prefactor, so I'm not putting it under integral, but in principle I've got to integrate the whole right-hand side part. And, well, the integral has got certain limits always. So let's say we consider the dynamics of a particle from a given moment of time that we're going to call 0 to a moment of time we're going to call time t. And the velocity will change from some initial value to v of t that we've got defined. A question?
Why is it that we treat the electric field as if it's a constant?
Oh, I assumed. Yeah, it's a good point. I assumed that it's a constant. So assume E is a constant in space.
So does this, is this one in particular sort of a nifty way to do it with a uniform field?
Yeah, that's that's a good point, and thanks for noticing this. It's that's an important point. And please tell me your name after the class. Just I promised I'll be awarding bonus points for questions that help me clarify important points. So, start doing that. So yeah, that applies to a uniform field. So a uniform field, that's a field that's it's constant in space, and if it is constant, then we can put it outside of the integral. I just forgot to mention it at first. And well, if it is a constant, then we can take this integral, and so what we get is v of t minus v naught equals q over m e t by taking these two integrals. And so what we get in a uniform electric field, the particle gets accelerated with its velocity changing linearly in time. And in this week's discussion section, there will be a question to practice that. Well, I hope this makes sense. If not, if anything is confusing at all, just please do not hesitate to let me know, or to complain about whatever is confusing. But just in any case, there'll be some practice on that, and it's also part of the discussion section. And there are exercises both in the homework and just in the textbook, if you wish. All right. So in general, when a free particle is placed in an electric field, it gets accelerated. If the field is uniform, then its velocity changes with time linearly, as we've just obtained. And what's the natural situation in which we have a particle or a free particle exposed to an electric field? Well, that can naturally happen if we place a certain object next to a charged object, and in that test object there are free particles that are not strongly bound to atoms. And that brings us to how materials can react to electric fields. So based on the response of materials, based on the response of various substances to external electric fields, all materials could be separated into two classes, and I'll explain what happens in them microscopically. So I'll write here materials. There are two types of them: conductors and insulators. And the difference between them is that inside conductors, charges can move. Inside insulators, they cannot. So, well, all materials consist of atoms. And, in isolation, each atom is neutral, and each electron has a positively charged nucleus and an electron cloud that surrounds it. But now electrons may behave differently once you stick together many atoms and they form a crystal or just a solid state or a liquid. So in insulators, electrons are still strongly bound by atoms. So let me write it down. Electrons are bound by atoms. I should write nuclei. And stay in them indefinitely. So when you apply an electric field to an insulator, meaning you expose a piece of an insulator to the field of an external charged body, the electrons in that insulator cannot escape their atoms, and they just stay bound there, and there's no significant redistribution or motion of charges inside an insulator. So because all electrons are captured by atoms and destroyed, charges cannot move. In conductors, also called metals, electrons are not strongly bound by atoms. In fact, when atoms combine together, electrons detach from their atoms, and each electron, so that there's a fraction of electrons such that a particular electron does not belong to any particular atom. And then when you apply an electric field to such a material, the electrons are no longer bound, and they are free to move in the entire conductor, in the entire system. So I'll write here charges can move, and those charges are called free electrons. And we saw examples of that. So we saw videos and we saw demonstrations. So the demonstrations we saw is basically any piece of a dielectric, it could be amber, for example, which we charged, for example, by rubbing it against a sheet of silk, and that would induce some charges there, and those charges would stay there for a long time, and they will be pinned in a sense. They would not go anywhere, and that's true about a huge class of materials. Well, I'll write down some examples here. Amber, rubber, PVC, all the materials that are used in demonstrations of electrostatic phenomena. But we saw also a different behavior of metallic objects. Well, let's say this is an aluminium can. When it is exposed to an electric field, let's say there's an electric field in this direction next to it, let's say it's been brought close to a charged object which creates this field, then initially the aluminium can is neutral, but it creates it applies force to the electrons in that aluminium can, and those electrons, or at least there's a big fraction of electrons which are not bound by their atoms, and that they start to move and charges get redistributed in the aluminium can. And let's do a small exercise. Let's take maybe half a minute or a minute to think if an electric field is applied in this direction, which end of the can will be positively charged and which end of the can will be negatively charged. So let's take a minute to think about that. So you can talk to your neighbor if you wish to check your thoughts. Pardon? Oh, it has a given direction, and that shows its direction. It means that if you put a positive charge there, it will be directed like this. All right, let's check it. Well, there are several ways to see it, and one way to think about it. So let's say there's an electron somewhere in this can, and I'm drawing it outside of the can, but the logic will still apply. So if we have a negatively charged electron and the field is directed in this direction, then the force acting on it will be in this direction. So the electrons in the can, they want to go to the left, and they will accumulate there. So there will be a surplus of electrons here, and behind they will leave positively charged nuclei. Just one second. That is the nuclei that are not fully screened atoms that will lack one electron, and that will be the distribution of charges. A question?
That's because the E field shows where a positive test charge would go, like the E field lines. Is that what you mentioned?
Yes. Yeah. So if inside of this conductor positive charges were moving, we would have the same, interestingly, we would have the same effect in terms of which end gets positively charged, which end gets negatively charged. That's an interesting observation. From just conducting that experiment, we cannot tell the sign of the charges of the particles that are moving inside. All right, are there any questions about this? So I would like to emphasize that once you place a conductor and an electric field and charges get redistributed in it, because it gets charged non-uniformly, and that's called an induced charge. That induced charge will create an electric field of its own, here that electric field the electric field that they create will be directed opposite to the external electric field. So the charges inside the conductor move in such a way that they counter the external electric field. And when the system comes to equilibrium in this external field, then the field everywhere inside it has to vanish, because if in equilibrium it doesn't vanish, it means that the charges will be just moving there, and we haven't arrived in equilibrium. Does that make sense? Yes. All right, so we have 5 seconds left. I think that's a good point to stop.